In this video, I'll be covering source transformation, Thevenin and Norton's theorem, as well as the concept of maximum power transfer, which are extremely useful techniques for simplifying larger DC circuits and making them more usable and easier to analyze. So the first equivalency we're going to look at is called source transformation, which allows you to interchange between these two configurations, one with a voltage source in series with a single resistor and another with a current source in parallel with a single resistor. These are extremely common configurations, and knowing this transformation will allow you to simplify a circuit extremely quickly and gather any important information you might need about power transfer or whatever you may need. So to kind of show this equivalency, we're going to analyze the terminal behavior of these two circuits. And I've created a kind of graph here with I terminal, the current, and then V terminal, the voltage. And created a kind of axes here so we can kind of get a sort of behavior curve. So we're going to find some quantities here. We're going to start with the circuit on the left, and we're going to label this voltage here as Vs. This resistor here will be Rs, and then this kind of terminal voltage will be V terminal. And then we can define the current through the conductor as I terminal. So we're going to write a KVL for this loop here. So knowing that the voltage drops must sum to 0 because of KVL, we can say that Vs, voltage across here, and we can subtract the voltage across the resistor here, which according to Ohm's law is just the current through it, which is I terminal, and the resistor value. And then finally this kind of open circuit V terminal voltage. And that should sum to 0. And we're also, just to get the behavior at the kind of extremes, we're going to write this in terms of I terminal. And that will leave us this equation. Okay, so to get this kind of curve here, we're going to look at these sort of intercepts here. So for this first one, if we're on the I terminal axis here, that means that V terminal is equal to 0. So this term will cancel out, and that leaves us, this point here is Vs over Rs. And that makes sense because if we short this voltage here, that means the voltage V terminal is 0, which is what we're doing here, and that would just leave us in Ohm's law here, which will be Vs over Rs for the current. And likewise here, if we're on the V terminal axis, that means I terminal is 0. So this term here would go to 0. And we would just be left with Vs equaling the terminal voltage. So the voltages here would be the same. And that also makes sense because if there's no current going through this resistor, there's no voltage drop, which means Vs is equal to V terminal. So those are kind of the endpoints of our circuit's terminal behavior. So likewise, we're going to analyze the terminal behavior of this circuit and create a kind of current and voltage graph here that will compare to the circuit on the left. So we're going to label this current source as Is. It's the current going through this branch. We're going to label this current as I terminal. Label the voltage as V terminal. And this resistor will be Rp. Now because of this junction here and the independent voltage or current source, we're going to use KCL here. And again, KCL states that the sum of the currents entering a junction equals the sum of the currents exiting. So here we've defined Is as entering, and then this current here, which we can label as IR actually, exiting as well as I terminal exiting. So that means Is is equal to I terminal plus IR, although we're going to substitute IR here for V terminal divided by Rp. You can see that here. This is just Ohm's law. We can see the voltage across this resistor. It's just the terminal voltage here. And that will allow us to obtain our intercepts for our curve. So to obtain our intercepts, we're going to look at the end behavior. So as V terminal approaches 0, this term would go to 0, and that would leave us with I terminal equaling Is. Likewise, if I terminal approaches 0, we're left with is equaling v terminal over rp. And if we solve for v terminal, that would leave us with is times rp. So this is our curve here. Okay, so we've obtained here our terminal current and terminal voltage curves, which encapsulate all the information about the circuit's behavior at its terminals. And this is our equivalency here. We can see we can swap between these two values to change between these two circuit configurations. If we have the circuit on the left with a independent voltage source and a resistor in series, we can swap the configuration to be a independent current source in parallel with the resistor just by using these conversions here. So if we want to find the current value for the current source, we can simply divide the voltage source by the series resistor. And likewise, if we have this configuration on the right with a current source and its parallel resistor, if we want to obtain the voltage source that would give us the same terminal behavior, we simply can multiply the value of the current source and the resistor. And here the resistor values would change this would be the same with either configuration. Okay, so before we cover Thevenin and Norton's theorem, we're going to cover this maximum power transfer theorem, which is a big reason why we want to be able to simplify any circuit to resemble this. Being able to deliver the maximum power to a load is very useful in many applications, and getting this kind of simplified circuit model allows us to very easily find that resistance value that yields maximum power. So given some source voltage, which we'll label as V Thevenin, and some internal resistance, which we'll label as R Thevenin, we're trying to determine which resistance value for the load, which we'll label as RL, will deliver the maximum power to the load. Now this is not maximum efficiency, that's different. This is simply power. So this theorem gives us kind of a formal proof of what value will yield, at least for DC circuits. So we're trying to maximize the power to the load, which we should write out as its formula. Now power through any component, you'll find V times R, that'll give you power, but you'll also find I squared times R, and V squared over R will also give you the values for power. And this is just something you can find from Ohm's law and some substitutions. In this proof, we're going to use this formulation, I squared times R, and that's the load we're trying to maximize. So we're going to do a substitution here, which is the current going through here, I. Now since we have a voltage and kind of a total resistance, the current through this will just be V Thevenin divided by the total resistance, which because they're in series is just their sum. So we're going to substitute this quantity here in for I squared, which after we distribute the exponent will just be V Thevenin squared times R Thevenin plus RL squared, and that's times RL. So we're trying to maximize this quantity, so we're going to take a derivative here and set it equal to 0. This is a way to do this. So quantity is PL, so we're going to take a derivative of PL, the power through the component, or the power the component's consuming, with respect to this resistance. So dPL over dPRL, or DRL. So this is a quotient rule because we have the component we're trying to find in the numerator and denominator. This is just a formula, which I'm not going to cover here, but you can find this in a variety of places. It'll just be the denominator times the derivative of the numerator, which in this case, V Thevenin squared times RL. That's just going to be V Thevenin squared, minus the numerator, V Thevenin squared, RL times the denominator, which will be 2 times R Thevenin plus RL. And that's all over the denominator squared, which in this case, it's already squared, so it'll be to the fourth power. Okay, great. So since this is derivative, we're going to maximize this by setting this derivative equal to 0. That'll give us kind of a maximum point if we were to graph it, or a minimum point, but in this case it ends up being a max. So if we set this equal to 0, this kind of whole expression, we can actually multiply the denominator out. So I'll just write it here for clarity. We can multiply this denominator on both sides, and that'll get rid of it on this side, and we're multiplying by 0 on the other side. So we're just left with this expression here, or this equation, and we can add this quantity to both sides to simplify further. We can solve for the value of RL here. So we see Thevenin squared appears in both these, so these will just cancel out. We can divide out that, and we're left with 2RL times R Thevenin plus R load equals R Thevenin plus R load squared. Now this expression appears twice, so we can cancel this out on this side and remove 1 from the power there. So we're left with 2RL equals R Thevenin plus RL. And we can subtract RL from both sides here. So that'll leave us with RL equals R Thevenin. And this is our sort of proof. So what this means here is that if we have some source with an internal resistance, in this case we've modeled as Thevenin and R Thevenin for the internal resistance, if we want to maximize the power delivered to a load, we need to have the resistance of a load equal the internal resistance of the source. And so we can show that in the next example. So for DC circuits like this example, it's simple. We found that it's just equal to the internal resistance if we want to deliver the maximum power. But for AC circuits, when you're dealing with impedances that have complex components, it actually turns out to be the complex conjugate of that value. So for this circuit, we'll perform Thevenin's theorem. Now, when doing this theorem, you can elect any two terminals from the circuit. So they could be these terminals, they could be these terminals. These terminals, it really is arbitrary what you choose, but the end goal is to get that simplified circuit model here with some independent voltage source and then some load resistance. So this will be Thevenin and then R Thevenin. This is the end goal. So for this circuit, we'll actually perform it at these two terminals. So we're trying to replicate the circuit's behavior, but kind of simplify it so it looks like this. Now the first step is to determine what the actual voltage is across these two terminals, what the potential difference is. Now you can do this with any method you choose. I have videos on node method and mesh method. I won't go through the full extensive walkthrough, but the first step always is to determine what your voltage is here, and that's your Thevenin voltage. So here I'm simply doing mesh current method. I'm assigning these meshes a current variable, and then I'm creating two system of equations, as well as that super mesh equation from the center current source. Again, you can use whatever method you like. Just the objective here is to find out what the voltage is at those two terminals. So here, once I've solved for these mesh currents, I can use these currents to find the voltage across this terminal by adding up the voltage drops across that 3 ohm and 16 ohm resistor. And so you do those calculations, and they'll give you the Thevenin voltage. So that'll end up being 66.6 volts, which will be the voltage source for our simplified model. So we found V Thevenin, but now we need to find the Thevenin resistance. So for the Thevenin resistance, it involves deactivating the independent sources. So in this case, the independent voltage or current source and the independent voltage source, and then determining the equivalent resistance as seen from these terminals. So we've already determined the Thevenin voltage. Put that up here as 66.6 volts. But we need to find the equivalent resistance, which is R Thevenin, as seen from these terminals. So the first step to do that is we're going to rewrite the circuit. We're going to deactivate these independent sources. Now, when deactivating sources, you have to be careful, depending on which source it is, what it means to deactivate a source. So in this case, for the voltage source, we always short voltage sources. So if we have some independent voltage source and we need to deactivate it, that just results in us shorting those terminals. For a current source, we want to deactivate it means to have no current going through that branch. So in that case, if we have a current source, deactivating it means actually opening the circuit at those two terminals. So using those kind of guidelines, we can rewrite this circuit. So we keep our resistors. But we're going to deactivate this kind of middle current source by opening it. And then these resistors down here will stay. And then for this 1 volt voltage source, we'll actually just short these terminals. And again, we're trying to find the equivalent resistance as seen from these terminals. So we can bring back these resistance values here. And again, we're trying to find the equivalent resistance as seen from these terminals. And that's our Thevenin. So if we look closer, we can see that these resistors are all in series in this outer branch. So that can simplify to a single resistance, which is just their sum. And that'll end up being 52 ohms. Again, it's from these terminals. And this branch here will just be the sum of those two resistances, so that'll be a single 19 ohm resistor. And we can simplify this further. This is just a parallel combination, which for parallel resistors, the equivalent resistance is just this formula. And for two resistors, you can simplify this algebraically to just get the product of their resistances over their sum. So after performing that, you should get a resistance value of 13.92 ohms. And this is our Thevenin resistance. So after we've obtained that, we have our kind of Thevenin voltage and Thevenin resistance, so we can complete the circuit model. These real quick, and then so again, our simplified Thevenin circuit will have a voltage of 66.6 volts and then a Thevenin resistance of 13.92 ohms. So this is the completed Thevenin circuit, and this simplification allows us to kind of perform some load analysis. If we were to, say, attach some load to these two terminals of this more complex circuit, it is essentially modeled by this simplified circuit with all the information encapsulated here. So if we were to connect a load to these two terminals, this is the kind of source voltage that would be supplied, as well as the internal resistance that would be seen. So again, This kind of Thevenin theorem allows us to simplify a much more complex circuit into something much more simple. And for Norton's theorem, that states that simplification gives us a independent current source in parallel with a single resistor, as opposed to Thevenin's. Now here we've covered source transformation, so we can swap between these two configurations really quickly using those equivalencies we found. So this kind of this Norton current, is actually just the Thevenin voltage divided by our Thevenin resistance, and that was found from source transformation. So if we do that here, we'll find that the circuit's current will be 4.79 amps, and then again from source transformation, our R Norton is actually equal to our R Thevenin here, so the resistance would remain the same, and these two models are equivalent, at least from the terminals. The behavior is the same, and they're indistinguishable. So this is Norton circuit, and this is Thevenin circuit. Now there's also an alternative way to find I Norton. You could short these two terminals here and find the resultant current through here, and that would also give you I Norton. But since we've covered source transformation, that's a very easy way to swap between these two circuits. So just to summarize, again, if you have any complex circuit, we can represent that with this box. This could be any circuit with any combination of resistors and independent current source, voltage source, or dependent voltage and current source, which we will do an example later. If we want to find some simplification from some terminals, say V, in this case we determined to do these two terminals, you can always represent them as either their Thevenin or Norton equivalent circuit.